Okay, today let's have a look at chapter 1, lesson 4, introducing derivatives. So first, let's have a look at the learning goals for today. After this lesson, you are expected to understand the definition and notation of the derivative of a function and the concept of differentiable at a point or on an interval. Second, determine a derivative of a function using the first principles definition. Third, understand the concepts of one-sided derivatives and their connections with the two-sided derivative of function. Then understand the relationship between differentiability and continuity of a function. Then identify the locations on a function where the derivative does not exist and explain why. Last, obtain the formulas to calculate the derivatives for constant functions and power functions and use these shortcuts to solve related problems. Okay, first, let's give it a quick recap of the instantaneous rate of change. So in our previous lessons, we have discussed the definition of instantaneous rate of change, which is given a function fx and two adjacent points px, fx, and qx plus h, f plus h. Then we define the slope of the secant between p and q is delta y over delta x, right? Which is actually simplified to the ratio between fx plus h minus fx over h, where h is not zero. Okay, note that when h approaches zero, the ratio between delta y over delta x should approach the slope of the tangent line at p, right? Understand? Then this limit is actually called the instantaneous rate of change, or the derivative of fx at point p. So this is a definition of the derivative of function at a certain point, denoted as the limit of fx plus h minus fx over h as h approaches zero. So here, this is actually the definition of derivative of a function. Be careful with this definition here. And we denote this limit as the derivative of fx, f prime x, fx prime, or dy by dx. Both of these two notations are the derivative of fx. Okay, so let's have a look at the definition and notation of the derivative more formally. First, let's have a look at the first principles definition of derivative. Derivative of function fx is actually a new function fx prime, defined by the derivative of fx, f prime, equals the limit of fx plus h minus fx over h as h approaches zero, if the limit exists. Remember that for functions, the limit does not necessarily exist at every point, right? So basically, the derivative of a function at a certain point is defined using the limit. You understand? That's why we spent 2 lessons there on the limit. So note that the fx prime means the derivative of fx at any x value that is in the function's domain, whereas fa prime means the value of the derivative of fx at the certain point where x equals a. Okay, you should be able to tell the difference. Then fx prime is actually called the Lagrange notation. And also note that the process of finding the derivative is called differentiation. Get yourself familiar with the terms here, okay? The process of finding the derivative is called differentiation. Okay, then we have a second type of notation for the derivative, which is called Leibniz notation. Leibniz notation expresses that derivative of the function y equals fx as dy by dx, read as dy by dx. This is also the derivative of y with respect to x. Leibniz form can also be written as that form here, dy dfx by dx. This means the derivative of fx. The expression dy by dx when x equals a in Leibniz notation means determine the value of the derivative when x equals a. Are we clear? And sometimes in some books, you can also see that there are two parentheses when you write dx by dfx by dx here, such as this and this. Sometimes they don't write parentheses outside fx, sometimes they do, but they are all acceptable. Okay, you understand? Any questions? Okay, so basically this is the concept of the derivative of a function fx. There are two notations. You can use either the Lagrange notation, which is fx prime, or the Leibniz notation, which is dy by dx, or dfx by dx, which means the derivative of fx or derivative of y with respect to x. You understand? Once this limit is simplified by letting h approaches 0, the resulting expression is expressed in terms of x. We can use this expression to determine the derivative of the function at any x value that is in the function's domain. Okay, next let's have a look at an example to illustrate this concept here. Okay, this example asks you to find a derivative using the first principles definition. Remember, the first principles definition states that the derivative of function is defined by a limit of a ratio, right? What the ratio is? The ratio is fx plus h minus fh, sorry, the fx plus h minus fx divided by h, right? Okay, so let's consider these three questions here. First, state the domain of the function fx equals x cubed, x squared. Then use the first principles definition to determine the derivative of fx equals x squared. What is the derivative's domain? Remember, derivative of function is also function, right? Question C. What do you notice about the nature of the derivative? Describe the relationship between the function and its derivative. Okay, I'll give you 2 minutes to have a look at this question here. Can you find the derivative of this function using its definition, specifically the first principles definition? Can start now. Okay, let's repeat the whole process. Okay, first of all, let's have a look at the solution here. First of all, the domain of this function is obvious, which is a whole real number set. Second, in order to find this derivative, we should use the first principle note definition, right? First principle definition states that the derivative of fx, noted by fx prime, is defined as a limit of the expression there, fx plus h minus fx over h when h approaches 0. That's the definition of the derivative of fx at any point x. You understand? And then we can just evaluate what is fx plus h. Fx plus h is just x plus h squared because we know the expression of fx, right? Then fx equals x squared. Then we expand everything and cancels x squared there. That gives us the original expression equals limit of 2xh plus h squared over h when h approaches 0. Apparently, we can cancel h in numerator and denominator. Therefore, we get the limit of 2x plus h when h approaches 0. Do you understand? Then this function is a polynomial function. When h approaches 0, that function approaches that limit approaches 2x, right? Therefore, by definition, the derivative of this function at any point x equals 2x. 2x is called the derivative of the original function. How do you understand? This is how we find the derivative of a function. Okay, question C. Notice that the derivative is also a function. The independent variable is x. The original function fx equals x squared is quadratic. Its derivative fx prime equals 2x is linear. The derivative represents the slope of the tangent or instantaneous rate of change on the curve, right? This is the definition of derivative. So you can substitute any value x into the derivative to find the instantaneous rate of change at corresponding point on the graph of the original function. Do you understand? Oh. All right, then let's do another practice. Use first principles to differentiate fx equals x cubed. State domain of the function and its derivative. Determine the following and interpret the results. Determine the questions of the tangent lines. Determine the equations of the tangent lines that correspond to the values you find in part C. Oh, this is actually not part C, should be in the previous. Question. All right, let's have a look at the solution here. First of all, we can find the derivative of this function using the first principle definition, right? Okay, so the derivative of this function, look at the whiteboard. Fx prime is defined using a limit of fx plus h minus fx over h, right? Then we should evaluate what is fx plus h and what is fx. Luckily, we know the expression of fx. Therefore, fx plus h is just x plus h cubed, right? Then minus fx. fx is x cubed. Then expand x plus h cubed to the very long expression here. Can you do that? We have already learned how to do this, right? Okay, so if we expand that, you will get a very long expression here. Then minus x cubed. Then x cubed is canceled with each other. Then combine all the similar terms. This will give you the limit of 3x squared h plus 3xh squared plus h cubed over h when h approaches 0, right? When h approaches 0 means h is is a number that is very close to 0 but not 0. Then we can actually cancel the h in the numerator and denominator position. That will give you, let's continue, the limit of the function 3x squared plus 3xh plus x plus h squared, right? When h approaches 0, the later two parts are both zeros, right? Therefore, the limit of this function becomes 3x squared. Can you see that? You see that? Therefore, the derivative or derivative function of the original function is 3x squared. Now the conclusion is the derivative of fx equals x cubed is fx prime equals 3x squared. So limit exists for any value of x. So the domain of the derivative fx prime is also x belongs to the real number set. You understand? Okay, now let's consider the next question. It asks us to find the equation of the tangent line at these points. Okay, first, we can calculate the derivative of this function at x equals 0, negative 2, x equals 0, and x equals 1, right? You can just plug that value in to find the derivative of this function at such points. Remember that the derivative of a function at a certain point is actually the instantaneous rate of change or the slope of the tangent line at that point, right? So first, the derivative of fx at negative 2, x equals negative 2. That means f prime negative 2 equals 3 times negative 2 squared, which is 12. That means the slope of the tangent line to fx at x equals negative 2 is 12. You understand? And similarly, we have f prime 0 is 0. That means the slope of the tangent line to fx is 0. And f prime 1 is 3, means the slope of a tangent line to fx is 3. Then, if you know the slope of a line and one point on the line, of course, you can write the equation of that line, right? For example, let's consider this first question. When x equals negative 2, first you can calculate the value of the function y equals negative 8, right? Just insert x equals 2 to that expression. Then the tangent point is negative 2, negative 8. Then we know, according to the equation of the function, the equation of that function is y minus y1 equals m times x minus x1. This is the equation of that function, right? X1, Y1 is a known point on the graph of that line. M is the slope, right? So here we know X1, Y1 is just -2, -8. Just plug them in. And M is the slope of this line, which is also known to us, right? Because we have just solved it. Then this equation is simplified to y equals 12x plus 16. For the second question, when x is 0, y 0, you can substitute x, y equals 0, 0, and m equals 0. The equation of the tangent is actually a horizontal line, y equals 0. See that? And then for the next point, when x is 1, y is 1, you can substitute x, y, 1, 1, and m equals 3. Then the equation of the line is y equals 3x minus 2. Therefore, the equation of the tangent is y equals x minus 2 at the point 1, 1. You understand? Any questions? Any questions? No? Okay. Then let's see another important concept. Remember that derivative is defined using limits, right? For limits, we have both one-sided limits and double-sided limits, right? Similarly, for derivatives, we have one-sided derivatives as well. So first, let's have a look at the definition of one-sided derivatives. Okay, first, derivative of function fx at any x value is defined by f prime x equals the limit of x plus h minus fx over h as h approaches 0, right? This is called the definition of derivative of a function fx at any point x. Then we can define the left-hand derivative of a function fx at any x value by the following expression. The left-hand derivative is defined as the limit of this function as h approaches 0 from the left side, which is denoted by this symbol here. Okay, this is called the left-hand derivative. Similarly, this should be right. The right-hand derivative there is a typo. The right-hand derivative of a function fx at any x value is defined as the limit of that ratio when h approaches 0 from the right side, which is denoted by f prime x plus, which is here. This is called the right-hand derivative. This is called the left-hand derivative. This is called the derivative. You understand? Okay. The reason we introduce the one-sided derivative is to introduce a concept of differentiable on the interval. So let's have a look at the concept of differentiable or differentiability. First, a function fx is differentiable at a point A if the derivative of this function at point A exists. That means f prime A exists. Next, a function fx is differentiable on the open interval A to B exclusive if it is differentiable at every point in this interval. So this is a definition of differentiability on the open interval, okay? Be careful with the word here, open interval. Next, a function fx is differentiable on a closed interval a to b inclusive if it is differentiable on the open interval ab and both the left side derivative at a and left side derivative at b exist. Okay, there are 3 levels of differentiability we can define. So be careful with the differences here. Okay, at a point or on an open interval or on a closed interval. Okay, what they mean here. Okay. You need to be cautious that let f be a function that has a derivative at every point in its domain. You can then define a function that maps every point x to the value of the derivative of f at x. This function is written as f prime, and it's called the derivative function or the derivative of f. Sometimes f has a derivative at most, but not all points of its domain. The function whose value at a equals f prime a whenever f prime a is defined, and elsewhere is undefined, is also called the derivative of f. It is still a function, but its domain may be smaller than the domain of f. Okay, then next, let's have a look at the connection between derivative and left-right derivatives. So when we learn the limits, we have a theorem that states that the limit of function at a certain point exists if and only if the left limit and right limit both exist and they are equal, right? So similarly, we have a theorem that connects the derivative and the right and left derivatives. We have the following theorem, which says that the derivative of fx, f prime x, which is defined as the limit of that function when h approaches 0, equals d if and only if, which means this symbol here, if and only if the left derivative at this point equals d, and the right hand derivative of this function also equals d. You understand? Because derivatives are defined using limits. So most of the properties for limits also applies to the derivatives, right? A consequence is that if the one-sided derivatives are different at a certain point, then the two-sided derivatives does not exist at this point, often denoted as DNE. Understand? Okay, let's see an example to illustrate this concept. Okay, first, find the left-hand, right-hand, and two-sided derivative, if exists, of the function fx equals the square root of x squared at the point where x equals 0. Okay, I'll give you a hint. This is actually a piecewise function. You can simplify that to fx equals either x when x is greater than or equal to 0, or fx equals negative x when x is smaller than 0, right? So can you find the left hand, right hand derivatives first and decide whether the derivative of this function exists at the point where x equals 0? Okay, I'll give you 2 minutes to think about this question here. Yeah, let's have a look at the solution here. If you want to find the left hand and right hand derivatives, you can just use the definition, right? First of all, as we said, this function can be simplified to a piecewise function. Fx equals x when x is greater than or equal to 0, and fx equals negative x when x is smaller than 0. Therefore, the left-hand derivative f prime 0 equals the limit of f0 plus h minus f0 over h when h approaches 0 from the left side, right? When h approaches 0 from the left side, which expression you need to use? Apparently, this point is to the left of x equals 0. Therefore, you should use the second expression here, right? Then fh is actually negative h. f0 is 0. Therefore, the limit becomes the limit of negative h over h when h approaches 0 from the negative side, from the left side. And the left derivative is negative 1. Can you see that? You understand now? And then let's find its right-hand derivative. Right-hand derivative is defined at x equals 0 is defined as the limit of f0 plus h minus f0 over h as h approaches 0 from the right side, which can be simplified to fh minus f0 over h as h approaches 0, the limit. Then this is the limit of, so now what is fh? Remember that here f approaches 0 from the right side, right? If h approaches 0 from the right side, that means you should use this expression to evaluate fh, which is h itself. You understand? Because here h is a positive number. A positive number is is x itself. Therefore, fh is h, and f0 is 0. So that becomes h over h, which is 1. Therefore, the right derivative at this point, x equals 0, is 1, right? And therefore, you can say at x equals 0, this point, the left derivative does not equal the right derivative. Therefore, the derivative at x equals 0 does not exist. Therefore, we have the following expression for the derivative of this function. The derivative of this function y prime equals 1 if x is greater than 0, negative 1 if x is less than 0, and undefined at this point x equals 0. You understand? You understand now? Okay. Any questions? Okay, if no questions, let's have a look at another theorem, which states the connection between differentiable and continuous. Can you recall the concept of continuity of a function at a certain point? The function is continuous at a certain point x equals a, if and only if the three conditions are met, right? First, the function must be defined at this point. Second, the limit of this function must exist at this point. Third, the limit of this function as x approaches this point must equal the value of the function when x equals that point, right? You understand? So that's the definition of continuity at a single point. Then, what is the connection between differentiable and continuous? We have the following conclusions. First, if fx is differentiable at x equals a, then fx must be continuous at x equals a. However, the reverse statement is not necessarily true, which means if fx is continuous at x equals a, fx is not necessarily differentiable at x equals a. Understand? So the proof of this theorem is not covered in this course. That involves some more knowledge about the derivatives, which you will probably learn in your university study. Okay. So currently, we'll just treat it as a conclusion. You can use this conclusion to solve some problems. Okay, so actually this theorem can be proved like this. So it's not required in this course, but if you are interested, you can have a look at the proof after this class, okay? I'm not gonna discuss this in depth here. If you are interested in the proof of that theorem, you can have a look at the proof after this class, okay? I'll upload my video onto my YouTube channel. You can check that out with class. And for the second part of the theorem, you can easily find a counterexample, right? The second part of the theorem states if fx is continuous at x equals a, fx is not necessarily differentiable at x equals a, right? A typical example is what we have done to this question here. We know that if fx equals the absolute value of x, then the graph of this function looks like this, right? Which is continuous in the whole domain, but it's not differentiable at location where x equals 0. You understand? Okay. Okay, so next we have just talked about a function the derivative of function can be non-exist, right? So next, let's have a look at some typical conditions where the derivative of function cannot exist. So for example, if we have a function y equals fx, the derivative does not exist at x if there is a discontinuity x1, or there is a typo, exists. The following four graphs shows that where the derivative of this function does not exist. So in the first graph, if there is a discontinuity at x1, x2, x3, then because it's discontinuous, according to the theorem we have just talked about, this function is of course not differentiable at these points, right? In the second graph, it says that sometimes you will have a vertical tangent, such as in the x4 here, in the position of x4 here. Then at this point, this function is also not differentiable. And in the third graph, sometimes we have a cusp, which means this function is not differentiable at x5. And sometimes we have a corner, such as the function we have just talked about, right? Y equals the absolute value of x. And at such point, this function is not differentiable as well. Okay, so let's make a summary. Sometimes one encounters a point in the domain of a function, y equals fx, where there is no derivative. Because there is no tangent line, in order for the notion of the tangent line at a point to make sense, the curve must be smooth at that point. This means that if you imagine a particle traveling at some steady speed along the curve, then the particle does not experience an abrupt change of direction. Okay, in order for the function to be differentiable at a certain point, at that point, the function must be smooth. Okay. This means Okay, we have just listed some typical examples, right? There are 4 types of situations you should be aware of. Either first one, discontinuities. Second one, vertical tangents. Third one, cusps. And last one, corners. Okay. For example, in the second examples, we can have a function like y equals, for example, x to the power of 1/3. This function will have a cusp. Sorry, we'll have a vertical tangent at x equals 0. Because that derivative does not exist at this point. Okay, we'll talk about more of this in our following lessons. So far, as long as you know there are 4 typical conditions where the derivative of function does not exist, it's okay. Okay, any questions? All right, then last, let's have a look at the derivative of basic elementary functions. First of all, let's give it a quick recap of the definition of elementary functions. Okay, first, all elementary functions are continuous at any point where they are defined. So we can use this property to evaluate the derivative of a to find the limit of the elementary function, right? So next, let's have a look at the definition of elementary functions. An elementary function is a function built from a finite number of compositions and combinations using 4 operations: addition, subtraction, multiplication, and division over basic elementary functions. The set of basic elementary functions includes, for example, algebraic polynomial. Second, rational fractions. Third, power functions. Fourth, exponential functions. Fifth, logarithmic functions. Sixth, trigonometric functions. Seventh, inverse trigonometric functions. Eighth, hyperbolic functions. Ninth, inverse hyperbolic functions. So these are typical types of elementary functions. Sorry, these are typical type of basic elementary functions. And based on the basic elementary functions, using addition, subtraction, multiplication, and division, you can also have elementary functions, more elementary functions. Then in our following lessons, we'll talk about the derivative, the shortcut to get the derivative of the elementary functions. So today we'll focus on the constant function and the power function. So next, let's have a look at the derivatives of these 2 types of functions. Okay, first, let's have a look at the derivative of a constant function. So we have the following theorem to help us define the derivative of a constant function. Let C be a constant, then fx equals C is a constant function, right? Then we have the derivative of this constant function, f prime x, is always 0. Or we say df by dx is 0. So actually, you can prove this theorem very easily by using the definition of derivatives. So here, let's have a look at the proof here. We can let fx be equal c be a constant function. By the definition of derivative, we have the following equation. The derivative of this function f prime x equals the limit of fx plus h minus fx over h as h approaches 0, right? So what is fx plus h? Because it's a constant function, we have fx plus h is c, and fx is also c, right? Therefore, the limit becomes the limit of c minus c over h as h approaches 0, which is actually the limit of 0 as h approaches 0, which is 0, right? Therefore, you can see the derivative of a constant function is always 0 at any point in the domain. Understand? This is very easy to understand, right? It's pretty straightforward because constant function is parallel to x-axis. There is no change at all. Therefore, the instantaneous rate of change should be 0 at any point. Okay, then let's have a look at the derivative of a second type of elementary function, which is a power function. Then we have, again, we have the following theorem. First, the derivative of a power function when the power number is a positive integer exponent. If fx equals x to the power of n, where n is a positive integer, then we have the derivative of this function f prime x equals n times x to the power of n minus 1. Or we say dfx by dx equals n times x to the power of n minus 1. Well, actually, this theorem can be extended to more general cases where n is not only a positive integer, but can be any real number. Therefore, we say, if fx, we have the second theorem. If fx is a power function, x to the power of n, where n is any real number, this theorem also holds true. Then the derivative of fx equals n times x, n times x to the power of n minus 1. Or dfx by dx equals n times x to the power of n minus 1. It turns out that the power rule holds for any real number n. However, the proof of the power rule for the general case is a bit more difficult to prove and will be omitted here in this course. Well, actually, we can prove the first theorem very easily. We can prove the first one, okay? When n is a positive integer, this is very easy. So this is a proof of the first theorem. Again, it's not required in this course, but if you are interested, you can have a look at the proof after this class. If you have any questions, we can discuss the proof after this class, okay? Just have a look at that. Actually, we can prove that for any power function, the derivative of this power function is n times x to the power of n minus 1. Okay, so based what we have learned for the constant function and power functions, let's have a look at an example of how we can use the shortcut method to find the derivatives of constant functions or power functions. Okay, here, I'll give you 2 minutes to have a look at this question. All right, have you finished? Let's have a look at the solutions. Okay, first question, first function is a constant function. Therefore, for constant function, its derivative is 0 at any point, right? Therefore, we have the derivative of x, f prime x, is always 0. And the domain of this derivative is from negative infinity to positive infinity. Next function, why it's C here? All right, this should be B. Okay, this should be B and this should be C. The derivative of this function, this is a power function, right? Therefore, the derivative of power function is we can put the power number in front, becomes the coefficient of the derivative. Therefore, the derivative function is 4x cubed. And apparently, as you can observe here, the domain of the derivative also from negative infinity to positive infinity. Next, fx equals x to the power of 1/3. Also, this is the power function, right? For power function, the derivative is 1/3 of x times 1/3 minus 1. Reduce the power number by 1. Then it becomes 1/3 times x to the power of -2/3. This is acceptable. You can stop here. Also, you can convert that to a form of ratio, which is 1/3 times x squared, then find its cubic root. This is also acceptable. You understand? You can choose either way. And as you can see here from this expression, x cannot be 0, otherwise you will have a 0 as the denominator, right? Therefore, the domain of the derivative is negative infinity to 0, union with 0 to positive infinity. Okay, last, the function is fx equals x to the power of -3, right? Therefore, this is also a power function. The derivative of this function equals -3 put in front, then reduce the power number by 1. That becomes -3 times x to the power of -4, which is which can also be expressed as -3 over x to the power of 4. Again, x cannot be 0. Therefore, the domain is negative infinity to 0, union with 0 to positive infinity. You understand? Do you understand? Okay. So if you have a more complex expression like this, for example, if we have y equals okay, I'll write it here. If you have an expression like what happened there? Okay, suppose if I give you a more complex expression, y equals 20 negative x to the power of 5, then find the square root. You should also be able to find its derivative, okay? You understand? So in essence, this expression is also a power function, right? You understand? Yes or no? If I give you an expression like this, okay, let's use a simple one. Y equals 1 over x to the power of 5, then find its square root. This is also a power function, right? You understand? This can be expressed as x to the power of 5 over 2. Then dy by dx is 5 over 2, then x to the power of 3 over 2. Do you understand? Oh, sorry, I lost the -1 here, right? This should be a negative 5/2, and then this should be negative 7/2. You understand? I mean, if I give you a more complex expression, y equals 1/x to the power of 5, then find its square root. Can you find dy by dx? Can you do that? So first of all, we convert this function to y equals x to the power of 5/2, right? All right, this should be negative, right? Then dy by dx is negative 5/2 times x to the power of negative 5/2, then minus 1, which is negative 5/2 times x to the power of negative 7/2. You understand? Okay, so basically this is the end of today's class. So let's have a look at the learning goals again. Now, after this class, you should be able to understand the definition of notation of the derivative of a function and the concept of differentiable at a point or on an interval, whether the interval is open or a closed. Second, determine a derivative of a function using the first principles definition. Okay. Third, understand the concepts of one-sided derivatives and their connections with the two-sided derivative of a function. Next, understand the relationship between differentiability and continuity of a function. Next, identify the locations on the function where the derivative does not exist and explain why. Last, obtain the formulas to calculate the derivatives for constant functions and power functions. Remember, we have learned the two shortcuts for constant functions and power functions today, right? For any other functions you haven't learned, you can refer to the first principle definition to find its derivatives, okay? All right, so class dismissed. I'll see you next class.